Clausius-Clapeyron equation describes the change in vapor pressure of a conforming liquid to its changing temperature in a closed system. So the original expression shown here, derived from the laws of thermodynamics and conservation of energy, relates the change in pressure, vapor pressure, as a function of changing temperature to the latent heat of the phase change, the vaporization, the energy transferred, an energy term here, an enthalpy term, divided by the Kelvin temperature divided by the changing volume. So this isn't the expression that we normally do calculations with, where we have a pressure 1, a pressure 2, a temperature 1, and a temperature 2. But we can get to that expression by manipulating the original thermodynamic expression that we see here. And so one note that we will originally, or that we'll kind of observe here before we get started, is the relationship between the vapor pressure and temperature is not linear. But we can get a linear form that matches experimental data by integrating an expression we derive from the original. So here it is, the change in natural log of pressure as a function of temperature equals the molar heat of vaporization divided by the ideal gas constant and temperature squared. And so looking at this, we see that that delta V term has disappeared. So let's talk about that as part of our simplification of our expression. So delta V, the change in volume of the phase change, is the volume of the resulting vapor from the volume of the liquid, and we're going to make the assumption that that liquid's compressed, the vapor is highly expanded, and so it's close to zero relative to that vapor, very small relative to the volume of the vapor. So we're going to just get rid of that term and leave the vapor volume left over. And so then if we subtract, or excuse me, if we note that volume of an ideal gas, we'll make an assumption that our vapor behaves like an ideal gas and use another thermodynamic expression that we're used to, PV equals nRT. We can actually solve for volume, nRT over pressure, to get an expression we can plug in for volume in our Clausius-Clapeyron expression. So let's do that. Let's go ahead and plug that in, okay, and take a look at this new expression that we get and make some observations about it. Okay, I've got some helpful expressions we're going to use momentarily over to the right there. Not too bad. A little bit of calculus won't hurt us here. But if we take our original expression, plug in for volume, nRT over P, we get a new expression of H over nRT squared, and then we can bring P to the top, pressure to the top there, all right? And so from there, I can make a note, hey, look at this. H over N is actually the molar enthalpy of vaporization. That's where that term comes from. And this R over T squared term remains on the bottom. So now I can actually say that dP dt equals the molar heat of vaporization over, or times pressure, over RT squared. And I can divide both sides by pressure, and I can say that 1 over P dP dt is equal to delta H of vaporization times RT squared. So I'm getting there. I've got this right-hand side looking somewhat useful to me at the moment. And now I want to use one of my useful expressions that I've put over here. The dln of x over dx equals 1 over x. So I can take 1 over P and actually replace it with dln x over dp, so dln of p over dp, because these two terms are equal to one another, times dp dt, and I can set that equal to delta H of vaporization over RT squared. And so what we get from that is that dP cancels, and now I've got dln of P over dt equals delta H of vaporization over RT squared. Okay, and so at this point I've now gotten to an expression that looks a lot like what we had above. And from here, I'm going to integrate both sides with respect to temperature. Okay? And so what that's going to do is it's going to free up natural log of pressure, and then we can bring out constants. Remember, we assume that the molar enthalpy of vaporization doesn't change. We're going to bring out our R value there, and that's going to leave us with the integral of 1 over t squared dt. Okay, so we're again integrating as a function of temperature on both of these. Well, our helpful expression number 2 comes into play here, because now I can say that ln of P, just coming from the bottom there, ln of P is equal to the molar heat of vaporization divided by R, and that integral that we had, 1 over t squared, it's 1 over t to the minus 2. Well, it actually simplifies to an integral here of t to the minus 2 plus 1 over minus 2 plus 1 plus a constant. Okay, and so we know that we've got a constant in our expression here that we're going to leave to its own devices. Okay, further simplifying this, we get delta H of vaporization over R multiplied by minus 2 plus 1 is minus 1, minus 2 plus 1 is minus 1, and if we multiply through a constant, delta H of vaporization we assumed was constant, R is a constant, we multiply that through, we're still getting a constant when we multiply it by this constant here. So we're going to leave that labeled as C for something we're about to do coming up. Well, what does that give us overall? That gives us natural log of P is equal to negative, bring that negative out, that negative term out, delta H of vaporization over RT is equal to natural log of P, and all of that plus a constant there. So here plus a constant equals natural log of P. So this expression, y equals mx plus b, so plus a constant, matches our linear equation form if 1 over t is our x value, our dependent variable there. And so what, or excuse me, our independent variable. And so what we want to do then is do our before and after scenario now that we've got this linear expression after integration. So we can now look at two different temperatures for our linear expression, where we can say, well, the natural log of our pressure 1 is equal to negative delta H of vaporization over RT1 plus the constant. We can also look at natural log of pressure 2, just a second point here of reference. Vaporization is a constant, our molar heat of vaporization over RT2 plus this same constant. Now we can actually set these equal to the constant and set both before and after scenario 1 versus scenario 2 equal to each other. So let's finish out deriving the expression. So I'm going to say that the constant is equal to pressure 2 plus delta H of vaporization over RT2 equals the same constant is pressure 1, natural log of pressure 1, plus, just adding plus delta H of vaporization over the our temperature to both sides, T1, and setting those equal to each other. So I solve for constant here for P1, solve for the constant here for P2 and T2, and I set those equal to one another. Well, now I can subtract the natural log of pressure 1 from both sides, and I can subtract the delta H of vaporization of RT2 from both sides. So I just moved this over to the left side, moved this over to the right, and now we're getting there. So now I can see subtracting natural logs. One way we can combine those, the way we do combine those, is to set up a fraction, all within the natural log function. To the right-hand side, we would say that equals the right-hand side, but I'm going to pull out a negative delta H of vaporization over R, a constant, -1 times this constant. And what that's going to do is it's going to leave in this term 1 over T2 becomes a positive, minus this first term becomes a negative 1 over T1. And we finally derived our expression that we use in our calculations for vapor pressure in the Clausius-Clapeyron equation. Okay, finally, let's work through this example problem where we're calculating the vapor pressure in atmospheres of water at 30 degrees Celsius. Okay, and so the hint, remember the normal boiling point of water, we'll say that pressure 1 is 1 atmosphere as defined by the normal boiling point for a substance, and then we'll say that for water, that temperature 1 is 100 degrees Celsius. Well, if we convert that to Kelvin, add 273, we get 373.15 Kelvin. 273.15 plus 100 gives us our Kelvin temperature. We'll solve for P2, and we'll say that temperature 2, we said, was 30 degrees Celsius. Add 273.15, that's 303.15 Kelvin. So now we're ready to plug everything in and get our final answer here. So natural log of pressure 2, what we're solving for, divided by 1 atmosphere. We didn't have to do pressure 2 and pressure 1 as long as we keep consistent between 1s and 1s and 2s and 2s, we'll get the same answer on the other end. Okay, but as we define it over there, we're going to keep pressure 2 as our variable, our unknown variable. All right, negative delta H of vaporization of water, which we know to be 40.7 kilojoules per mole. Okay, so make that 40 here, 40.7 kilojoules per mole. And we're going to use the ideal gas constant, 8.314 joules per mole Kelvin. Well, I'm going to go ahead and convert that into kilojoules, 0.08314 kilojoules per mole Kelvin, so that we get our units matched up. And now we can multiply by our expression here, 1 over T2. Well, T2 is 30 degrees, so we wanted to make that our Kelvin temperature. Well, our temperature for the vapor pressure we're solving for, T2 and P2 match, minus 1 over T1, which we said was the normal boiling point of water. And so now we are ready to combine all these terms. So I will combine the terms on the right. We'll see that kilojoules cancel, moles cancel, 1 over Kelvin cancels with 1 over Kelvin. We're left with a whole number. We put that in the calculator all in one piece, negative 3.029. Okay, going a little bit extra out there just to maintain our sig figs. And now natural log of P2 over 1 atmosphere. We need to get the natural log function out, so we do that by raising both sides to the e. So e to the natural log of P2 over 1 atmosphere gets rid of the natural log function, and so we're left with P2 over 1 atmosphere equals e to the negative 3.029. We raise both sides to that exponential, and then that number we get is 0.0483. multiply both sides by atmospheres, by 1 atmosphere, and we get pressure 2 is 0.0483 atmospheres, the 3 significant figures, and we have a vapor pressure calculation for water at 30 degrees according to the Clausius-Clapeyron equation.